I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine a world where computers process information not with electrons, but with light, where data races through chips at the speed of photons, not the crawl of current. That future is being built right now through a breakthrough field called nonlinear integrated photonics. It's where light stops behaving linearly and starts interacting with itself, bending, mixing, and transforming in ways that can reshape the entire landscape of computing and communication. So what does nonlinear really mean? In most everyday materials, light passes through unchanged. That's linear optics. But in certain materials, when the light becomes intense enough, like from a laser, it actually changes the material's behavior. The material starts mixing light waves, doubling their frequency, or changing how fast they travel. This is what scientists call nonlinear optical effects, the magic behind technologies like ultrafast switches, laser frequency combs, and even quantum light sources. Now, the key to making all this work isn't just the clever design of chips, it's the materials that make them. They're the foundation of this revolution. To bring nonlinear optics onto a chip, you need materials that respond strongly to light, lose very little energy, and can still be made using semiconductor tools like the ones that make your phone's processor. Let's look at the materials leading this charge. First up is silicon. It's the backbone of modern electronics and photonics, and it offers powerful nonlinear properties, great for tasks like all optical switching. But it has a weakness. It tends to absorb too much light at the wavelengths used for telecom, producing unwanted heat. But recently, researchers at MIT have found a way to give silicon new life, creating devices that can double frequencies and modulate light without the usual losses. This could lead to ultra-fast, low-power optical circuits and even on-chip terahertz sources for secure communication. Then there's silicon nitride, or SiN. This material is fast becoming the favorite child of the photonics world. Why? It barely absorbs light, handles huge amounts of power, and works perfectly with existing chip-making processes. Teams in India have even built silicon nitride microring resonators, tiny structures that trap and amplify light like sound in a whispering gallery, opening the door to compact quantum light sources and ultra-efficient optical processors. Another star player is lithium niobate, a crystal famous for its lightning-fast electro-optic response. In its new thin film form, it can be integrated directly on chips, making it ideal for frequency conversion and high-speed modulators. Meanwhile, gallium arsenide and other 3V semiconductors combine strong nonlinearities with built-in light emission, perfect for compact lasers and quantum devices that need both power and precision. If we go beyond traditional semiconductors, we enter the exotic world of chalcogenide glasses, materials that can bend light with astonishing strength, generating broad spectra and ultra-fast signals, though they're a bit delicate. And emerging materials like aluminum gallium arsenide on insulator take things further, offering both high nonlinearity and tight control over dispersion, key for quantum light generation and precision metrology. Then come the real game changers, two-dimensional materials and metamaterials. Imagine atom-thin sheets like graphene or molybdenum disulfide that can twist and multiply light in surprising ways. Researchers have even strained graphene nanopillars to make them emit light at double frequencies, a feat once thought impossible. These discoveries could power quantum communication, secure data links, and nanoscale imaging systems. And just when you think the story ends there, researchers at NIST revealed tantalum pentoxide, or tantala, a new workhorse material that combines transparency, high refractive index, and low loss. It can generate light across a huge spectrum, from ultraviolet to infrared, making it perfect for compact frequency combs and broadband photonic chips. The next leap is hybrid integration, combining these materials like puzzle pieces: silicon for structure, lithium niobate for modulation, and graphene for speed. Together, they'll enable light-based chips that think faster, consume less power, and secure our data in ways electronics never could. Even new topological materials, which route light flawlessly around corners, are pushing us closer to the dream of true optical computing. This is the dawn of an optical era, where materials define capability. Every new discovery in nonlinear photonics is not just about faster communication, but about transforming how intelligence, defense, and technology itself operate. From space networks to quantum encryption, from AI accelerators to medical sensors, it all begins with mastering how light behaves in matter. We're not just bending light anymore, we're engineering it. And the materials behind nonlinear integrated photonics are building the future one photon at a time. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.